Hi students, this is video 23 in our electricity unit, and it is on circuit equations. Specifically, we're going to be covering Ohm's law and the power equation. The essential question that this video aims to answer is, what relationships and equations predict the movement of charges and energy in a circuit? So you can really only control two things in a circuit. The first thing that you can control is the voltage. And the voltage is determined by the battery that you use. So each battery has a specific voltage that depends on the chemical reaction that's going on inside of it. Most regular AA batteries that you are used to are 1.5 volts. So this means that the chemical reaction inside is giving 1.5 joules of energy to every coulomb of electrons that goes by. So as electrons go through each battery, they are picking up a little bit of energy as they go. And this means that if you want more voltage, one thing you can do in a circuit is you can add more batteries. So if the electrons go through one battery, they gain 1.5 volts. If they go through another battery and another battery, they're going to gain 1.5 volts, 1.5 volts. So they'll have a total of 4.5 joules of energy per each electron. Another thing you can do to change the voltage in a circuit is you could put in a different kind of battery. So lithium-ion batteries are another chemical reaction inside. Your cell phone has a type of lithium battery in the back of it. So depending on the kind of amount of voltage you want, you can add batteries or change the kind of battery that you have. The second thing that you can control in a circuit is its resistance. The resistance depends on the design of the circuit and the different devices that are inside. So something like the type of wire that you are using has a natural resistance that is included in the resistance of the circuit. Or if you have little resistors along your circuit, or resistors like light bulbs, for example. So if you want to add resistance to a circuit, you can add a resistor or change the design of the device, because the resistance is how hard it is for electrons to pass through. So in the circuit below, we have a 9-volt battery, and we have a couple LED lights, 3 LED lights along this circuit, which are like a type of resistor. And then you've got a plain old resistor up above in the top here. So we can, if we want to add more resistance to a circuit, we can add additional resistors along the path that those electrons are flowing. So given what we know about circuits, we can determine which of our variables in our circuit are independent and which are dependent. In a circuit, voltage and resistance are our dependent variables because, as we just talked about, their values depend on the actual hardware in the circuit, on the actual things we're putting into the circuit and how we're building it. So changing one of these things, like voltage, is not going to affect the resistance. If you change the battery, it doesn't make it harder for the electrons to go through, and vice versa. So the battery doesn't add resistance, and the resistance doesn't add or change voltage. Current and power, on the other hand, are what we call our dependent variables, because their values do depend on the voltage and resistance values that we have hardwired into the circuit. So if you change either the voltage or the resistance, or both current and power are going to change. In the next few slides, we're going to come up with the equations for current and power based on the relationships between these variables that we have just covered. So if we want to calculate current flowing through a circuit, what is one of the things we could do to increase the number of those electrons moving through the wires in a circuit each second? Well, one of the things I could do is I could add more batteries to this circuit. When you add more batteries, then every electron moving through the batteries is going to get more energy. If we think about this like the school day analogy, if you are getting more energy from your house, which is the battery in this situation, you're going to move faster through your day. So the more batteries we have, the faster this current is going to move through the circuit. More voltage equals more current. And since increasing the voltage leads to an increase in current, that means that voltage has a linear relationship with current. As one goes up, the other goes up. As one goes down, the other goes down. So our next question is, what would happen to the current in our circuit if we replaced our resistor, our light bulb there, with one with much higher resistance? So same battery, but a different light bulb that's much harder for electrons to pass through. Well, the higher the resistance of the light bulb, or the harder test, the fewer electrons are going to want to decide to move through that circuit. In terms of the school day analogy, if you have a choice between going through and taking an easy test or taking a more challenging test, most of the electrons are going to choose to take that easier test. So in this case, if resistance goes up, that means current is going to go down. The number of electrons flowing is going to go down. This is an inverse relationship between current and resistance of a circuit. These two relationships that we just talked about can be combined into one equation that we call Ohm's Law. So just to review, we know now that current has a linear relationship with voltage and an inverse relationship with resistance. Remember that the symbol for current is not intuitive, it's an I. The symbol for voltage is a V, and the symbol for resistance is an R. So given what we know now about the variable symbols and their relationships, take a minute to try and come up with Ohm's Law on your own. So what you should have come up with is that current is equal to voltage divided by resistance. There's a linear relationship between current and voltage, and there's an inverse relationship between current and resistance. Remember that voltage and resistance have no relationship because these are things that are hardwired into the circuit. One does not change the other. The second equation that we are building today is the electrical power equation. Remember that power is the change in energy every second. One way to think about power is to think about Halloween. Your house is the battery, and you're giving out energy as pieces of candy. The total power being produced depends on how many pieces of candy you're giving to each kid coming through and how fast those kids are coming through. So why do we care about power? In devices that we use, power is how much energy is being transformed into some other useful kind of energy each second. So if we're talking about power in terms of lights, more power means more light. More power can mean more sound. More power can mean more toast if you're talking about power in your toaster. So it's taking electrical energy and transforming it into some other kind of useful energy that we use. If we want to calculate the amount of power coming out of a battery or being used at a resistor, there's two ways that you can increase the amount of power that you have. The first is to increase the number of electrons moving through the circuit, which is another way of saying increase the current. if we have more electrons moving through the current and hence the resistors on them, then more total energy will be deposited on those resistors. So as you increase the current, we're going to increase the power, and that means there's a linear relationship between current and power. The other way that we could increase the power is you could increase the energy that you give to each electron, right? And this is what we call voltage. So we're increasing the voltage. If each electron is carrying more energy with it as it goes through, then more energy is going to be deposited at each resistor. So if we increase the voltage, we also increase the power. And that leads us to conclude that there's a linear relationship between voltage and power as well. So a good example of this, to increase the voltage, I might add another battery or another couple batteries. So if we're going to build our power equation for circuits, we've determined that power has a linear relationship with both current and with voltage. So take a minute to see if you can build this equation on your own. Power, symbol for power is P, symbol for current is I, symbol for voltage is V. So see if you can put the three of those together into one equation. Hopefully you came up with power equals current times voltage. So let's see if those units would make sense if we had units in with our numbers in this equation. So the units on current are coulombs per second, and we're multiplying those by the units on voltage, which is joules per coulomb. So that would give us coulomb joules per coulomb seconds. So our 2 coulombs will cancel out, which will leave us with joules per second. And another name for a joule each second is a watt. So let's revisit that essential question that we started off this video with, which is, what relationships and equations predict the movement of charges and energy in a circuit? So go back and review the variables we've talked about. Voltage and resistance are our independent variables. Current and power are the dependent ones. Review how we can use these relationships between the variables to come up with both Ohm's law and the power equation for circuits.